want to talk to you about waves. First thing I want to show you is this video clip here on the screen. So, real quick example, this is an explosion here, and I want you to see the shock wave, the wave traveling through the surface of the earth after this explosion. And there's something else I want you to notice too. You'll see it, and then you will hear it. Okay, so we'll talk about that. Take a look. There's the explosion. You see it traveling through the earth in the form of a wave, and then you hear it. Okay? I want to do it one more time. So watch the explosion, watch the light, and then you see the waves traveling along the surface of the earth there, and then you get it, and you hear it. And the reason why is that light travels a lot faster than sound, right? But they both travel in the form of waves. They're actually different types of waves we're going to talk about here in a second. Okay? I got this long spring right here, right? And I want to try to produce a wave for you guys real quick. So I want to get some energy to go through it, and then I want to create a standing wave pattern here. And what I want you to notice is you have a point where you get that maximum displacement, where it's highest away, where it's at its highest point. That's what we call the crest. And then you got its lowest point. That's what we call the trough. And we're going to talk about some other things within that wave diagram right now. But I was walking along the Greenway over there by Goat Island. There's this little swamp area back there, and I was like, hey, I'm gonna ask my son to throw a pebble in the water here and watch the ripples, the waves that form. Same type of idea. Guys, waves are forms of energy that are traveling through some sort of material, in this case, which we call the medium. Check this out. So there's the rock, okay? And it created this disturbance, this circular pattern, that is propagating from that original disturbance. I threw another rock over here too. But you see that wave, that disturbance traveling through that water right there. And then they actually interfere with each other a little bit, creating some wave patterns that I would love to get into at some point with you guys. A diagram of transverse wave for you really quickly. Check this out. Number 36, okay? The first thing that I would draw if I were you, okay, when you get to diagram a wave is, I'm going to draw this dashed line right here. And what I do is I call this rest position, okay, or just rest, right? That represents that water before we threw the rock into it. And then when we threw this rock into it, it created this disturbance, this pattern, where the water actually kind of went like this as the energy was traveling through it, okay? Now, the top part of the wave, we were just talking about that a little bit ago. That's what we call the crest. Hopefully you guys knew that at this point. If not, there you go. The bottom part is what we call the trough. Okay? So there's a trough over there. Now, question number 36 says we need to diagram rest position, crest, trough, wavelength, and amplitude. Okay? Now, wavelength, I like to refer to this wavelength is, it's exactly how it sounds. It's the length of the wave, okay? So you need two identical positions. I like to go crest to crest. So this distance right here is this Greek symbol called a lambda, and that's what we call wavelength, okay? And there's some important things with wavelength. Like you can start to get into like the velocity of a wave is equal to a wavelength multiplied by frequency. We'll get into all that stuff hopefully in a little bit, okay? All right, now, so we got crest, trough, we got rest position, lambda equal, that's your wavelength, and then amplitude is going to be this position from rest to crest. That's what we call amplitude, okay? Or you could go rest to trough. That's what we call amplitude also, but this would be a negative amplitude. This would be a positive amplitude, okay? All right, but that's a transverse wave. Now, here's the thing. What makes this a transverse wave? That's what we need to talk about next, and that's the next, that is the next question, this is the next part of question number 36. If you were standing, let's say you were standing right here as that shock wave came to you, okay? Your body, or let's say you're in the water, you're at the ocean, okay? Here comes this wave. Your body would kind of move up and down like that, okay? That's what I call the particle. That's what I call the particle movement, okay? But the energy of this wave is actually going to go this way, okay? So that's the energy of the wave. So the relationship between particle and energy, that's what we call a perpendicular relationship. When we'll put a little right angle symbol in there, that's what makes it a transverse wave. That's question number 36. 37, list the electromagnetic spectrum in order from longest wavelength to shortest wavelength. I'm going to do that really quickly here, but there's only a small section of the EM spectrum that we can actually see with the human eye. That's the visible light section. But there's so much more out here. If I take a wave, I'm going to draw this transverse wave. I'm going to draw my wavelengths, but as I go from left to right, I'm kind of squeezing these wavefront, the crests close together, which means we have a high frequency over here, okay? So this is high frequency. Over on this side, this is low frequency. Another way to look at that is we have short wavelength over here, and we'll put a lambda symbol there. And over here, we have long wavelength. I'm going to put that lambda symbol there for wavelength, okay? So here's the section of the electromagnetic spectrum. Maybe you've heard of them. Longest section here, radio waves, okay? So guys, and we have telescopes that go with every single one of these sections in the electromagnetic spectrum. We got radio waves, okay? And the next section, we have what we call microwaves, okay? So we got radio waves, microwaves. Now, not here yet to the visible light section yet, but right before the visible light spectrum, we have what we call infrared. And then past it, you have UV light. This is what happens when you get a bad sunburn. You're exposed to too much UV light. And then out here we have X-rays. And then finally, gamma. Gamma is out here. But there's your electromagnetic spectrum. And we have telescopes for every single one of those sections. Okay? I like to draw these little wavefronts here, okay? It's like a slinky, okay? I'm going to put them close together. I'm going to spread them out. I'm going to put them close together. I'm going to spread them out. So what I'm going to do is I'm just going to pull back on some of these coils here. Hold on to it tight. And then I'm going to release these, okay? And this is a pretty short slinky, so that's why it's going pretty fast. Let me just do like a couple of them here. So, and I'm going to pull back on a couple coils. I'm going to release them. Okay? So, the energy is actually vibrating, or the particles are vibrating back and forth, and then the energy is going the same exact direction, parallel. Okay? And so, that's what makes this a longitudinal wave, like sound wave. Compressions, rarefactions, and then we got another set of compressions right here, and then rarefactions over there. But here's the idea. Here's the important part. And this is what makes it a longitudinal wave. If the energy is going this way, okay, so the energy is, let's say, is going in that direction, okay? Well, the particles are going to vibrate back and forth like that. So this relationship to each other, those two relationships right there is what we call parallel, okay? This is parallel, making it longitudinal. This is transverse, making it energy. This is perpendicular, making it transverse, okay? Example for here is electromagnetic waves, okay? Light, that's what we use our telescopes for here. The example here for longitudinal, sound is probably the greatest example.